Okay. So we'll have this one in English. So I will just introduce you Ruben, which is a PhD student at USP. He's working on reinforcement learning, and he's also the organizer of PAPIS, which is like one of the biggest conference here in Sao Paulo on machine learning. So I will just let him do his talk. Thank you.
Thanks. Hi. Thanks for having me, Nubank. Today, I don't think I need to talk about me. If you're interested, I'm on LinkedIn, look me up. There's everything you need to know. Terry said all that's important. I'm talking a little bit about reinforcement learning today, specifically about one algorithm, the Q-learning algorithm, and then later about deep Q-learning, so we get something from a more recent past, including deep learning and reinforcement learning together. So I'm giving a short introduction to reinforcement learning, then Q-learning, what are the challenges for reinforcement learning in general, how we can use deep learning to overcome those challenges, and then I'm going into deep reinforcement learning, how it works in detail, and then if we have time, some extensions and what you can do if you are interested in reinforcement learning. This is all very familiar for me, so I'll probably be talking fast. And if you have questions, please raise your hand and ask the question. I might be too fast. I can't really judge you from here. Okay, so reinforcement learning is concerned with problems that are modeled as Markov decision processes. That means that we have an environment in which we want to learn a sequence of actions that helps us solve a given task. And we want to learn an optimal policy to solve that task. The general challenges for that are that it's, in the traditional reinforcement learning approach, is only for a very low dimensional space in respect to actions and states. It is very time consuming, so the agent needs a lot of examples to learn. And once you have learned to solve that task, it's task specific. You cannot easily transfer the knowledge that you've gained to another task. There are many existing algorithms for the traditional reinforcement learning that work very well, but only for smaller problems. So the most popular is Q-learning, but there's also SASA, Reinforce, Actor Critic, and many others as well. So the most popular algorithm is the Q-learning algorithm. The algorithm is here as it was published. Basically, it works like this. We have an agent that performs an action in an environment and receives an update from the environment in form of a reward and a follow-up state. The agent uses that state and decides with respect to the knowledge that he already has which action to take, and then he observes what he gets and updates a Q value that is a quality value for the state and the action that he's taking. And he does that a bazillion times. He has to do it a lot of times to get a good estimate for the quality of the action in that particular state. So if we look at the main formula here, every time he makes an update in a given state for a given action, we have a learning rate that's mu, or often it's also used as alpha, where we have the old value, and then we make an update of the value, giving the current observation of the reward, plus a future expectation of what he might get if he follows an optimal policy. And so the agent has to do that over and over again until he gets the Q values right, so he finds an optimal policy to act in the right way in every state that he encounters. To make this a little bit clearer, here's an example, which is like the standard example for reinforcement learning and Q-learning. We have an environment that's consisting of 6 states. Each of the blocks is one state. our task is to go from any state to the target state in the right lower corner, in the left lower corner. And so initially we don't know anything. So we put the agent there, he doesn't know what to do, he walks around blind, doesn't know anything. We apply reinforcement learning, and in the end he knows exactly from in every state what is the best action to get closer to the goal. Okay, so how does the agent do that? In the traditional reinforcement learning, the Q-learning was based on a tabular representation. So you can imagine that we have a table that has a row for every state and a column for every action in that state. Initially, you can initialize the values to 0 or randomly. That doesn't make a very big difference. So in this case, for this example, I initialized it to 0. And you can see when the agent gets to any of the states apart from the goal states, he receives a reward of 0. So nothing happens. He doesn't get a reward. But if he gets to the goal state, he gets 100 points. We have a discount factor, which we discount future rewards. So if a reward is further away, it is less worth to the agent. If it gets the reward in 1 step, he gets the full reward. If it would get it in 2 steps, the discount factor discounts that value according to that factor. So the Q value is calculated by the actual reward that he gets plus the discount factor times the maximum value of Qs that he has. Okay, let's go into the algorithm. So initially we randomly place the agent in one of the states. In this case, it's state 3, and we let him choose an action randomly. The action chose randomly to go down, which was very lucky because he immediately got to the goal, which gives him an immediately reward of 100. And in the goal state, he also he cannot get another reward because the goal state doesn't have a Q value. So the update of the Q value is here 100 because we were also setting the learning rate to 1 so that every iteration is immediate and it doesn't take so long to learn. Let's do a second round. This time the agent drops down in state 2 and decides to go to state 3, take the action right. The reward that he gets is 0, no reward for state 3. And then it chooses the maximum Q value of that state, which is 100, which we got from the update before, which is multiplied by the discount factor, which is 50. So the update for this state and taking the action right would be 50. So we do this a lot of times until it has seen all the states various times, and then we finally get this optimal policy that the agent needs to follow. And you can see that, like, taking from state 1 going right or going down is has the Q value with the highest value, so it makes sense for the agent to follow the highest Q value. And that's why we say the optimal policy is taking the action that has the highest Q value. Okay? So this is how general Q learning works. So this was a very simple environment, very low state space and low action space. If we're looking at more complex problems, we cannot use a tabular representation, right? This has 6 states. An Atari game, for example, if you want to learn that has millions of states. So you can't use a table. So just a reminder, we can use deep learning for that. And deep learning helps us because it gives us the opportunity to make a nonlinear transformation of the input data. We can have different levels of representation in the network. And it's very general. We don't have to hand engineer any features. So we just like put the network there, and the only thing that we have to give it is the network structure. We don't have to put any initial values. And the network is able to generalize to states that it hasn't seen before by having a very good generalization. The main factors for the success of deep learning recently is that we had like a massive increase of available data. We have increasing computational power and parallelization with all the GPUs and tensor units. And we also had like what is very important, advances in algorithms, as well as optimization methods, activation functions, network architectures, etc. Yeah, so that brings us to deep reinforcement learning. And so in deep reinforcement learning, we're combining deep learning and reinforcement learning. And what we do is we're using a deep neural network and replacing the Q table. And then through that, we generate an architecture that does end-to-end reinforcement learning. It gets as input only the input that we give him, the state representation, and it gives us the action that we want to take. The differences from Q learning, now we have the Q value is not only dependent on the state and the action, but it's also dependent on the weights or the parameters of the neural network that we're using. And the network loss function, this is very interesting, and this is what separates reinforcement learning from supervised learning. Where in supervised learning, you have the truth, you know what it should be, and then you have the output of your network and you can calculate the loss. And reinforcement learning is different because you don't know the target. You don't know exactly what value you want to have there. So we're using an approximation, which is the reward that we get in the step that we immediately take, plus the discounted Q value that we expect to get in the future. And so this value keeps changing, so the loss keeps also changing a lot. This deep reinforcement learning has a lot of challenges, and people tried to use neural networks for a while already, but with mixed results. Only a couple of years ago, DeepMind figured out how to make it stable and to learn things properly. So the biggest changes were that if you have data streams, that the data is sequential, so it's highly correlated. So if you look from one state to another, the changes in the state are very small. So it's very hard to learn something from that. And you can also see that in the network, when you train it, that slight parameter changes rapidly change the whole policy. And you don't know the reward in deep reinforcement learning. You don't know anything about the environment. You just say, this is the input, this is the actions that you can take, tell me how the environment works, and figure out how to behave optimally. But I don't tell you anything about the environment. And then another problem is that using only like static images would be very difficult as well. So to conquer these challenges, the first thing that they introduced was an experience replay. So that would decouple the learning and the acting of the agent. So the agent would act and would save its experiences in an experience replay. And then every couple of training steps, it would take these experiences from the memory and use that for training, and it would select those experiences randomly, so they would not be in sequence, but like distributed over the whole memory. So what it does to the loss function is it doesn't change anything in the later part, but you see that like it gets the expectation from D, which is the replay memory. and that helped to stabilize training a lot. The problem with the quick changes in the policy, they conquered by introducing a second network, which they call target network. So it's basically the same network as the other one, but the weights are not trained. So they are freezed for a given time, and only every couple of episodes you update the weights with the network that you are currently training. So we had to have a stable training signal for the agent. And that's how you get like this theta minus, which is the target network, which is fixed during training. So the reward scale is also unknown. That was something that was very difficult to handle. The thing that they did was just to clip the rewards to a sensible range from -1 to 1, which is in some cases okay, in some cases not okay, because if you have, like, for example, you want to shoot enemies and you have an enemy that gives 500 points and you have an enemy that gives 700 points or 10,000 points, for the agent they are the same. So it probably not all the time learns optimally in that case. It will learn to destroy both enemies, but it wouldn't give preference to one or the other. The next problem is the static images. So if you only see one image, it's the same for us as well. We don't know anything about the dynamics of what's going on here. So alone from this image, I can't really tell what's happening. So what they do is, like, they take a sequence of images so that it's clear that you have, like, information about the velocity, about the direction or acceleration. You can imagine like a bullet going through the screen. If you have like one image, it's just a point on the screen. If you have like several, you can see in which direction it goes, and also like from distance you can see how fast it goes, or if it goes faster. Yeah. The network that they used is a very simple convolutional neural network. As I said, the input is are 4 layers of 4 images. The input images are 84 times 84 pixel. And then they have 3 convolutional layers, 2 fully connected layers, and an output layer which has an action for all possible action that are available in Atari games, for example, or whatever environment you're training in. Okay, now that's what I said before. The training happens basically in 2 steps. The first step is acting in the environment, and you have the agent using the current network to perform an action. This action gets saved. The environment responds with an update of the state, which gets buffered and then put in the replay memory. Okay. There was a question?
The images that you pass through the convolutional, they're not color channels, they are sequential, like that previous comment. They're sequential images.
The images are passing through as a stack at once. You put the 4 images as a stack, and then you put it in a network.
Do you define a time window for this stack?
Yeah, so you can, yes, you can. What they actually do is they only take every 4th image, every 4th frame, and then they put these together, 4 of them as one state. So one state is actually like the duration of 16 frames, but only 4 of them are shown to the agent. Okay. Okay, so this is the first state where the agent, this is happening online. This is happening all the time. The agent is training in the network, is playing with the environment and making new experiences. The part that happens offline also happens every step, or if you want every few steps. This is where we use the second network, the target network, to train the agent. So this is the network that we keep updating all the time, right? And this one is the target network that is fixed. And we're taking the transitions from the replay memory, put them in the networks, calculate the loss, and update this network. And so this basically keeps happening at every step. So what you can do with this, at first you can see an agent here that is supposed to play this game, Breakout. And at the beginning you see it's very bad. It doesn't really know what to do. Sometimes it gets lucky. But over time, you can see here it's already better. It moves more around and gets the ball. After 400 episodes training, the agent is already pretty good, right? It's already it already plays better than me. But it's still not perfect. But if you train longer, the agent gets really clever and discovers like tricks and strategies to get more points even. And so here you can see that it discovers to go behind and make more points. And so this happens without the agent knowing anything about the environment before. It just knows like this is the pixel output of the screen. These are the actions that you can take. Here's the reward signal. Learn how to play the game. And then it gets to this kind of performance. There's a couple of extensions that came out in the meanwhile. Since we have a bit of time, we can talk about that. These are all, I think I'm going to talk about 3 of them. They are all pretty standard right now. The double DQN and the other one are the next one that I'm also talking about. They are very simple to implement because we already have everything that's needed for them in the regular implementation of the algorithm. The double DQN gives us gives us an option to have to decouple the action selection from the network and use the target network to only to calculate the quality value for the expectation that you have for the network. And just to show this here, you have the blue curve and the red curve. The blue curve is with the new algorithm, and the other one, the red one, is with the old algorithm. So what you can see is that after a while, the agent unlearns how to play the game and gets a bad score, while using the other one, it improves even the learning and gets a much higher score in the same as in the other game. This happens in games that are more complicated than the one that we showed before, when you have longer time until you have you get a reward. Then you need something like this to get a more stable training result. Something a little bit different is here in the dueling networks, where we don't actually calculate the Q value directly. We're calculating an advantage value for the algorithm first, which gives us an indication of how much taking one action is better than taking another action in a given state. So we basically calculate a value for the state I'm in and not for the state and the action. And then I'm calculating a second value that tells me which of to take one action is better than taking the other action. That gives also a better training signal. And another thing that's very popular right now is using a different kind of experience replay memory, where we don't have a like just like a random pick of the transitions that we choose from the memory, but a prioritized one. So we looking for memories or experiences that gives us more information, that have like a higher score, for example. So we know that we can learn more from these experiences than from others. So if you have like an experience that gives you 0 points, it's hard to learn from that. You learn from it too, but not as much as when you get like a reward, for example. And then you can like define some form of priority function that will give you a hint on how to act in the environment. But that's like also like very specific to the environment that you're in, and sometimes it needs a bit of tweaking and trying out what kind of priority you want to use. So there's much more extensions of this DQN. One that was published just like a year ago is the Rainbow, which combines basically all of them. And you can see like this gray one that we have here is the regular DQN, and then the other ones are individual extensions of it. And if you combine everything, you get a much higher performance than using just only the extensions. What they are showing here is the performance of playing Atari games, like I think like 50 or 60 Atari games, and the 100% is what a human would get normally too. So you can see that like in after I don't know 30 million frames, the computer plays superhuman Atari on like all the Atari games that are there. But there are some where it's much better, and but there's very few where it's worse than humans. So what can you do if you're interested in reinforcement learning? Most of the work, or like libraries and everything, are in Python. Using Anaconda for the environment is very good. I work a lot with notebooks. I use TensorFlow and PyTorch. Obviously, GitHub is a very good resource, not only to get stuff, but also like to share stuff. A very good selection of environments is in the OpenAI gym. You have any kind of games like Super Mario, you have robot simulations, Pac-Man, you can play Doom, you can have like physics simulator where you have like humanoids or spiders or whatever, which you can teach to move around obstacles, to run, these kind of things. You have like soccer simulator, and everything is included in the OpenAI gym and very simple to interface. And I think that's it. Unfortunately, pizza is not in here. Terry is not here too. Okay. So then, as Terry said, I'm also the organizer of Puppies.io. We're a series of machine learning conferences that we hold internationally. We had like this year we had one in London, one in Boston, and one in Sao Paulo. And next year we already have the date for the Sao Paulo conference. It's going to be our biggest puppies ever. There's going to be more than 500 people. It's going to be at Dafiti, and the date is in June 24 to 26. Already saved the date. We're going to very soon open the call for papers. Anyone can submit a proposal. We have a planned review phase where we select the papers that are presented, but we also have invited international speakers, like to have like the best of both, like the industry standard, but also like from academia. And yeah, we also have workshops, tutorials, demos. We have exhibition space for sponsors. And yeah, I hope I see a couple of you there as well. If you have questions, like come to me in the break or now. Yeah, thanks.
Any question?
Oh, and you can also ask in Portuguese. I do understand, but I speak very bad.
Oh, hello. Good evening. I wanted to know, what is your PhD about?
So my PhD is about transfer learning for reinforcement learning. So you can think of it as like, if I have already learned how to solve one task, what can I take from this task to learn a second task faster? Like, what is the knowledge that I can transfer from one task to another? That's basically it.
Hi. Does it have any difference between this kind of games and I don't know if you're aware of that initiative that they are using reinforcement learning or deep learning to play Dota.
They're using deep reinforcement learning for that, yeah.
Because in this kind of games you have the score increasing every time, and there you have humans playing against machines, and the match can be the machines thinking that they are winning, and then everything can change. So the scores goes down in some time of the match. So is there any difference between?
Yeah, so it's a little bit more complex. Mostly because you don't have the full information about the environment, right? You have things that happen somewhere on the map that you can't see. Like here, you can, like in Atari games, you see everything, and then there's nothing hidden. In this kind of games, you have some hidden information that's important for the state, but you don't have information about it. So that's a little bit of a greater challenge. In principle, you also use reinforcement learning for that, but you have only because it's you don't have an MDP, which I said in the beginning, a Markov decision process. You have only a partial observable Markov decision process, which makes it more difficult to learn. And they are not using like a straightforward implementation like this. They're trying to have special agents that, for example, learn how to do specific things very good, and then they have another agent that can decide which agent of those special things would be useful in this particular moment, for example. But there's a variety of different architectures that are more complex than this one, yeah.
Hi. How can we use it? I made my question in Portuguese, ok?
Sure.
Como é que a gente pode usar reinforcement learning na indústria em geral, num banco? Tem algum caso de uso que você conhece?
Yeah. So one thing that reinforcement learning is used for is for the selection of network architectures, for example. So if you want to build a network and you have a lot of data and big data, you want to find a network structure that gives you good results, but it's also not too big, right? You don't want to, you gotta save resources for training, but also for if you want to implement them. And so there's approaches from reinforcement learning where they learn a network infrastructure. So they learn how to build the network. The agent selects what kind of layers you want to have and the network parameters and everything. That's one of the applications that's very general. A very applied application is, for example, Google uses reinforcement learning for their data centers to balance the server load. And by using reinforcement learning, they were able to reduce their electricity bill by 40%. And what that means for Google, that's a lot of money. And you can use it a lot for these kind of optimization problems because the agent learns how to how to behave in a good way to maximize the reward. So you can use it a lot for different kinds of optimization problems as well.
Okay, thank you.
I have a question. Did you order the pizza?
It's on the way. So I don't know, like 5-10 minutes, and we should have them.
Okay,
So thanks a lot.